Hi, everybody. This is a video about parametric equations, and we're actually getting into today projectile motion. So our objective is to use parametric equations to model horizontal and vertical components of motion along a curve in a plane. We're going to keep it really simple. I'm going to have links for how we derive the formulas and where everything comes from. But again, because everything has to be a little bit condensed right now, we're going to keep it pretty basic. So we're going to just do some examples. You have your homework, your formative, and then don't forget about your week 1 and week 2 things as well. So what this will help with will be questions 6 and 7 on your homework if you haven't done them yet. And then just a few reminders if you want to pause and read this slide. Okay. So why is studying projectile motion and how we use parametrics to model it, why is that important? There are so many applications of projectile motion. I can't even fit them all on this page. Ballistics, missiles, rocket launches, all of these things in real life have applications that have to do with projectile motion. So kicking a soccer ball, hitting a baseball, punting a football, and then the examples I mentioned before. So parametric motion or projectile motion is all around us. And the fact that it can be modeled by parametric equations is pretty cool. So let's get into it. So a little bit of vocabulary. So what is a projectile? A projectile is any object thrown by the exertion of a force. It can be an object launched into space and allowed to move free under the influence of gravity and air resistance. So again, thinking about kicking a soccer ball or firing a missile, anything that you launch goes up and then comes back down. Trajectory is the path followed by a projectile flying or an object moving under the action of given forces. Okay, so some formulas, these are in your formula sheet. And again, like I said, I'm posting this video. This is where this link is in your slides of how to look at how these formulas are derived there. It's very cool, but again, we don't really have too much time to get into it. And this video already exists in terms of deriving formulas. So if you want to click and watch this video and it will teach you where all these formulas come from, that's great. The best I'm going to do in this short video is just explain to you where what each piece of the formula means. So these are parametric equations, as you're familiar with, right? We have x as a function of t and y as a function of t. And again, they're connected. T is the same t, so t is time. So up here we have x equals initial velocity cosine of theta times t, and that represents our horizontal displacement. And you can see I've made a little triangle, or I've pasted in here a little triangle, right? The this horizontal line segment here is basically the adjacent side of the triangle to theta, right? So cosine of theta would be this side over the initial velocity. So if you just multiplied both sides by the initial velocity, you get x equals velocity cosine of theta. So that's where that comes from. And then vertical displacement is a function of time. So your height, basically, if you're talking about a projectile, this first term, negative 16 t squared, basically means the effect of gravity. So 32 feet per second, 1/2 times 32 feet per second is where this is derived from. So this will be always consistently a negative 16, okay, t squared. Then we have velocity sine of theta, which is similar to the velocity cosine of theta that we had for horizontal displacement. So velocity, initial velocity sine theta t plus h of 0, which just means your initial height. So this equation is a little bit more complicated because, again, gravity works on vertical displacement, right? It's pulling objects back down to Earth, and your initial height matters because that's going to impact how high off the ground you start at. So it's going to impact your how far high or low you are. Right. So again, a few parameters defined here. V0 is your initial velocity, theta is your angle of launch, and h of 0 is your initial height. So we'll do a few examples. So example 1, Ray launches a pumpkin at an angle of 65 degrees. I don't know if you've ever seen pumpkin chunkin. It's a thing. People build machines to launch pumpkins to see how far they will go. Launches a pumpkin at an angle 65 degrees from the horizontal with initial velocity of 75 feet per second. Write a set of parametric equations modeling the scenario. Round your coefficients to 3 decimal places. All right, so from the ground means my initial height is 0. So the first good step would be to go through your problem and match up your information to the parameters. So it's telling me from the ground, so h sub 0, initial height is 0. Angle of launch is 65 degrees from the horizontal, initial velocity is 75 feet per second. So I have, that should be V sub 0, but that's the idea. So V sub 0 is, there we go, 75. So write a set of parametric equations modeling the scenario, round coefficients to 3 decimal places. All right, so X is initial velocity cosine of theta t, so 75 cosine 65t. Y is negative 16t squared plus 75 sine of 65t plus 0. And then if I'm rounding my coefficients to 3 decimal places, then the coefficient to t here will be, remember I need to be in degree mode for this unit, degree mode, 31.696t. And then my 75 sine 65 will round to 67.976t. And I don't really need that plus 0, but there it is, okay? So that's, again, we just need to write the set of parametric equations. We don't need to figure out whose pumpkin won, when it was at its maximum height. We don't really need to do any of that for the purposes of this year. We're just learning how to write the set of parametric equations. Here's example 2. Arthur hit a tennis ball at angle 5 from the horizontal. Initial velocity is 100 feet per second. Ball is 4 feet from the ground when it's hit. Write a set of parametric equations modeling the scenario. Round your coefficients to 3 decimal places. See if you can do that. Oh, that's Arthur Ashe, by the way. So see if you can do that. Pause the video and try it. All right, and here's the answer. So we've got 100 cosine 5t. Negative 16t squared plus 100 sine 5t plus 4. Here the initial height is actually 4, so it's not 0. All right. The last example, and this is a little bit extra because we don't really need to do it for this year, but it's how you would, if you wanted to eliminate the parameter. Remember, we would solve for t and then substitute that equation in for x. So if we, for t, excuse me, we solve for t and then substitute this expression that we got by solving for t, we substitute that in to the y equation for everywhere that t is, right? So I just want to show you that that is connecting back to our lesson on Tuesday, but we don't really, again, you don't need to master this. It's showing you that this will actually be, this equation that we've written here is the actual trajectory of the ball. Okay, so this is the actual trajectory of the ball in space. Okay, this is the rectangular equation. Okay. One more thing I want to show you, and this is just a little, just for fun. It's, again, you don't need to know it, just a little fun to learn. We learned last class about eliminating the parameter, and I actually want to show you in this class about how to add a parameter. So if we draw, let's say we draw and label a vector v with tail at 1, 2 and tip at 3, 6. So you can draw it on your own if you want. I'm going to draw it here. So 1, 2, and then 3, 6. Okay, so this is vector v. Okay, can we write, so what if we had to write parametric equations where when t equals 0, x equals 1, and y equals 2, and then when t equals 1, x equals 3, and y equals 6. Okay, so there is a way to do that, and I'm just going to show you. So here is the point 1, 2. So this is where time is 0. And then here is the point 3, 6, where time is 1. Okay. And so what we can think about is for this vector v, it doesn't start on the origin, but we can still figure out its components. Okay. Its horizontal component, we see, since we go from 0 to 3, I'm sorry, from 1 to 3, our horizontal component is 2. And then our vertical component is 4. Okay. So this vector v has components of 2 and 4. And that's actually how we can determine our parametric equation. Okay, we start at, for our x equation, we start at x equals 1, right, when time is equal to 0. Okay, and then we add 2 each time t moves forward 1. Okay, because our x component is 2 for this vector. So we take that component and put it into this spot right here. And then for our y equation, we started off at y equals 2. So when time was 0, our y was equal to 2. And then our y component, right, between time 0 and time 1, the y component grew 4, right? So the y component moved 4. So we're going to put 4t up in here in this spot. And what's pretty cool is that if you then wanted to eliminate the parameter, the way we learned on Tuesday, you can, right? You solve this equation for t, you get t equals x minus 1 over 2. Turn around and plug that equation into the y. So 2 plus 4 x minus 1 over 2. Right, so when we solve that, that becomes 2x minus 4 times negative 1 is negative 4, so 2. Cancel the 2's, and then we have y equals 2x as our rectangular equation. And if we actually did continue graphing this line, it would in fact be the model, the linear model for this equation would be y equals 2x, right? Because if you continued down with the slope of 2, your y-intercept would be 0, and your slope would be 2. So y equals, if you're just going to use y equals mx plus b with a line, you have y equals 2x plus 0 or y equals 2x. So I just wanted to show you how you can use your initial point in a vector and the components moving from to the right and up, or to the left, to the right and down, however you're moving to get your components of your vector. You can use that to write parametric equations. Again, this is extended. It's just a little kind of like for fun for now. It might be useful for you if you go on to higher levels of calc, but I just wanted to show you that just like we eliminated the parameter on Tuesday, you can also put a parameter in. So I hope that that was interesting and fun for you. Thank you very much for watching, and I will see you another time. Have a great one.